Okay, hey everyone. Today we'll be going through a programming problem called the gathering children problem. This was a problem D, which is the fourth problem on one of the beginner contests on AdCoder in 2019. So it's a little while back, so problems have gotten a bit harder. So this might be a bit of an easier D, but we'll go through this. So it says that there's there's a string consisting of L and R, which just means there's all it can contain is just the characters L and R. That's the only thing it's allowed to contain. They could have probably worded that a bit better, but that's what they mean. It says there's n is the length of the string, and there are n squares arranged from left to right, and the ith character of s from the left is written on the ith square from the left. So all it's saying is the squares have the exact same symbols as the string in that order as well. So now it also says that the character written on the leftmost square is always R, and the character written on the rightmost square is always L. So that means this sort of string is not valid, and it actually needs to start with R and end with L. So it could be left, left, right, left, left, right, left, for example. First one's R, last one's L. That's valid. Okay, and then it says one child is standing on each square. So now we have a group of children, all of them standing on child wants to stand here, two here, and so on. And it says each child will perform the move below 10 to the 100 Google times. I guess doesn't really matter. What they're trying to say is this is extremely large. So we probably need to have some. We're not going to simulate this directly, but I think there's probably some like looping invariant or something that can lead to that we can use to figure this out. Okay, move one square in the direction specified by the character written in the square on which the child is standing. L denotes left and R denotes right. And then it says find the number of children standing on each square after the children perform the moves. Okay, so let's consider this example. Let's say this child starts at R. They go to L, then they go to R, and L, and R, and they sort of do this loop forever. But same with the child here. The child 2 would jump to R, then loop back and forth. What about this person? Well, they go to L, and then the loop starts again because they now reach this L and they start going to R and then jump back and forth. And if you look at this child 4, same thing, but on a different loop. It's like here, keeps jumping back and forth. And this person as well. And this person will do the same. So as we can see, we actually don't even need to care about the 10 to the 100. We probably just need to care about the fact that it's even, because there's a loop of 2 that every single thing will form from the looks of it. Every single child will enter some loop of 2 so far. So I think we can observe that every child enters a loop. Now, can we prove this? I think we can. Let's take cases. Let's say they start at the left. They start here. They will keep jumping left till they reach an R. If they reach an R, the last L and that R will form a loop. I think that's a pretty logical statement to make, right? So let's say they start with some L, make some jumps, all L, and then you reach the first R here. Once that happens, these two form a loop. Now we'll show that R exists. Suppose that R does not exist. Well, what happens then? Then you can keep going left forever. Or then you can start at the square with L and go left and go all the way to the left of the square, left endpoint without a right. Because if you're only jumping left until the end, you will reach the left endpoint at some point. But we know that the left endpoint is R. This is therefore it's a contradiction. Therefore we have a contradiction. So that's the proof. That means every child will enter a loop. In case 1L, they will always reach a right and they'll enter a loop. And then you can make a similar argument for right. You just go to the right and at some point you'll hit a L. Because if you don't hit an L, that would mean there's no left endpoint here. So same logic as above. Now that we know that it's each loop, each child will enter a loop, how do we know which loop it is? I think we can observe that this left loop, if a square is left, the loop will be to the left of it. And if the square is right, the loop will be to the right of it. Is L loop will be to left of it, and similarly, and vice versa for R. And a lot of the arguments we make today will be symmetric. Okay, let's say a child is at L. Proof. Child is at L. Let's say we know. Suppose child is at L. We already know. We know child will enter a loop. But they must jump left. They can't jump right. Travel to the right of their current point. Right? Their square is left. So no matter if they come back to that square, they have to go left. They can't go right from the current point. The starting point. Therefore, the loop will be to the left. And similar argument can be made for the right side one. And that means if we hit each block, this is the final observation. This is going to help us basically do the algorithm. Each block starts at R and ends at an L. What I mean by a block is a set of characters that have the same. I should define a block. Set of characters with the same loop. And then I think this is quite intuitive. You can probably prove this on your own. That means we can run an algorithm like this. A string, let's say we have a string like this. The algorithm will be something like this. Okay, you start block, and you know at the end, like it's 10 to the 100. That's huge. That you'll reach for each block. Each square will enter either the say the block looks something like this. Each square will end at one of the two central squares. The central squares will be like the point where the R's and the L's meet. So how we do is start block, and we keep track of a few variables. Center for start. We keep center, which we start at just 0th index relative to block. And let's define this as the start of the loop. So in this case, the center would be the start, which is the right one. That'll be the one index. Center will be 1 here. We also keep track of the length of the block. What we say is if it's length of blocks is 5, that means it's asymmetric. That means one of these central squares will have more. In particular, it'll be this one because these two will both be equivalent. Why are those two equivalent? I mean, if you think about it, let's say child starts at left, they'll reach this left in 2 squares. And just like that, this left will be at going left, right, left, and it'll be at left after 2 squares. Same here, right, right, left, they'll be at left after 2 squares. So these children will be at the exact same position. If they're in an even number of steps away, they'll be at the same position after an even number of steps. And since the loop is even numbered, they'll just remain in that position. And same thing for these two. So we have two groups really. These two, it's the 2 skips basically. Every 2 skip, and that would mean if the length of the block is even, we assign the if the length of the block is odd, the odd numbers, or which when you 0 index them, become the even terms. This is the third term. The odd terms are the majority, right? If it's 5, 1, 3, 5, but since this is 0 index, it's actually the opposite. It's the even numbers that will have a majority. So this would imply the center square would have just length of block divided by 2, and the other block will have 3. You can actually keep yeah, you can maybe keep track of the length better. I think you need to keep track of the start of the block as well, because you want to zero index it. So if it's like the 7th index, you can minus 7 from the start of the block to make it the 0 index. So keep track of the block start as well. I think I didn't consider that. And block end or length, they're both the same. They're both identical if you keep track of them. And you can just traverse through it. So you can start here, then you go, okay, well, the block starts here, 0, keep going, you hit R, okay, and then whenever you hit an L, that's the point before that's the center, so 0 would be the center because this is the loop, and then you end the block here, and then before you move on to processing the rest of the string, you quickly decide how many will end up here and how many will end up here, and then you come here. Then you go, oh, well, this block loop is like this, and then you just do this, and you come here, you do the same thing. So that's the algorithm. Yeah, so give it a go to implement this and see how you find it.